Hello friends, my name is Kamal Sarma. I'm a senior structural engineer in USA. Before that, I was in Assam Engineering College as a faculty for 13 years. Just like two other classes, I would like to talk about theory of structures, the basics. And you remember yesterday or last time, I discussed the three axes. Okay, here we have x-axis, this is y-axis, and this is z or z-axis. Okay, in United States we call it z, but in India and UK, etc., it is called z. But it's same. If I by mistake, if I say it is z, you understand it is that. But anyway, so this is a three axis I talked about last time. Many people may not have that perceptions, okay? What is the three dimensional, okay? First of all, I would like to demonstrate a box. This is a box. This box has, this is your x-axis, this is x-axis, the length, the height is your y-axis, and the breadth or width is your z-axis or z-axis. So this is, in reality, we have got a three-dimensional. All these objects can be represented by the three axes, x, y, z. But this is very important, these three-dimensional three axes, because you will see in future when we discuss the complex structures, we have a structure like this, we have a structure like this, this is a space frame or space truss, you can say. It's a truss, just like a structure like that. So every point here, we call it node. Considering matrix structural analysis, these will be your element. Okay, in finite element method, a beam probably you will have small number of elements divided into small number of elements, and every point is called nodes. But point is this, all these are reference to this x-axis. Here x1, y1 and z1. Here x2, y2, z2. These are the coordinates we have to give it with reference to the x, y and z axis. Okay? And we will give, this is a member A. We will define this member A with a connectivity, the A equal to, if it is number, is the node 1 and node 2. So A is a between A1 and 2. So very easily we can number the nodes and define all the members. And they are reference mix from this y, x, y and z. And this axis is called global axis. And each member has its own axis. This is your x1, probably This is your perpendicular to, this is your y1, and this is your z1. Each member has its own axis, like this, just like a member like this. Just like a member like this. This is your x-axis. This is your y-axis. This is z-axis or z-axis. So same way each member, and they are called local axis. Local. Local axis. And if we know the angle between this axis and this axis, theta, by trigonometric relationship, we can find out, we can convert the local axis to global axis. So that is why the XY coordinate is very important for a structural, especially in modeling, computer modeling. You should remember that. Later on we will be showing you, but at this moment you don't need it. It's very complex. And this type of complex structures you cannot solve by hand. So that is the reason we have simple structures. I will tell you what it is. This is a three-dimensional structure, right? X, Y, and Z axis. But if we take away the Z axis, only we keep an X and Y, that means XY plane. If we have XY plane, then our analysis will be easier. So all the basic preliminary steps will be analyzing structures with XY plane, the x-axis and y-axis. But later on, you will learn how to model a 3D complex structure, space frames, space structures, truss like that. Okay? So now we have to talk about the equilibrium. Okay, that is very important. Equilibrium is a state at static condition. Balanced by equal and opposite forces. It's a state at rest, static condition or at rest. Balanced by equal and opposite forces. So what happens, I just explained it with the help of a very simple example. Then you will understand. Okay? So you have a box, just like the box I showed you just now. This is your z-axis or z-axis. You have this is a box. Okay? Now this box is filled up with some heavy stuff, maybe books or iron rods. They are very heavy. They are really very heavy. So what happens? That is resting on the floor. Understand? They're resting on the floor. This is floor. You are applying a force F to push it, to move it, to slide over the floor. This is floor. So it will not move. Why? Because there is a frictional force that opposes it, that opposes your force, your push. So if this is the weight, W is the weight, then this force will be mu W, the opposing force, maximum. This is the maximum. Maximum force is that. So long your F is smaller than your mu W. Mu is your coefficient of friction. This is the coefficient of friction of this material of the box with the against the floor material, maybe concrete or maybe timber floor, doesn't matter. But this is the thing. So the mu actually for cardboard box is probably 0.5 against concrete floor. So you see, this will be almost half, 0.5 of W. This is the load. It's opposing. So long as this is F is smaller than FW, this box will not move. So what we can say at that point is there will be opposing reaction. Also F. Either that jerk mu W. No, that's the maximum it can have. But when you push it with a force of F, another opposing force is applied by this box through the friction, which is they are equal. Though this box doesn't go anywhere, it stays there. That is, it is called static equilibrium. It doesn't go. But as soon as you ask somebody to help you to push it so as soon as this becomes greater than FW, you break the equilibrium. There is no equilibrium. It is moving. It will be moving like that. So that means there is a capacity of the box to resist mu W, and this is the capacity, this is the frictional capacity of this box. So long as your F is smaller than frictional capacity, the structure remains in equilibrium. That means a static condition without any moving, without go anywhere. Same thing applies to structure. Okay? Same thing applies to structure. If you have a beam, you say this is a simply supported beam. Of course, it is also resting over pin, so there should be another force there. This is roller. So when you apply some force, this is reaction. Though I don't like to confuse you. This is the force. This will bend. You know that. This will bend. It is still in this equilibrium. This member has the moment capacity. That is maximum moment it can take. Because of moment, what is the moment actually? first of all, let me tell you what moment is. When you put an F there will be reaction R1 and R2. Say it is in the middle. So from here to here, the length is L. L because F is exactly at the middle, the half, it will be half of that, F upon 2, F upon 2. Exactly, because it is symmetrical. Then, your moment at any point is, suppose any point x. At this case, F upon 2 into x. This is moment. What happens to the structure as a whole? It will bend and it will, you see, when it bends, the top part is concave, that means it shortens. These fibers is shortens and other fibers elongates. So this side will be tension, this side is compression. So you will have stresses developing like that. This side it is tension below, compression top. But this is so far good, this is less than allowed. That is permission. I will come to that later on, how to calculate that. But what happens when it bends at one point, it will break. That means when it exceeds the stress, Fy, say it is the maximum allowable stress, Fy, yield stress, it will break or it will go down harder. There is no equilibrium. So that means this section has a moment capacity. So it's a moment capacity. The structural member all has a particular section. Suppose if you have definite breadth and depth, for this particular size, it has a moment capacity depending on this material. It's a moment capacity. Similarly, if the structure, same structure, as I have discussed. Your F is there, force, the reaction is F upon 2, F upon 2 is the reaction. What happens? This force try to shear. This is shearing it from here to here, no force is there. At this point, if you consider any point here, consider any point, any section here, any section X. This is still dominant, nothing is there, so it will be pushing up, right? And this force, this will try, do not let it go up. So what will happen? So it will try to break this section like this. This is shear. Shear is maximum near the support, and so you will have mostly failure here. Shear failure. Okay? How shear acts, I will tell you with an example. This is, you see this one? This is again a cardboard. So shear is, I'm pushing it up, it is pushing it down. It will break like this, see? 2 part. Right? So that is shear failure. It is shear always acts transverse to the axis. If this is the axis, it acts transverse to the axis. So depending on the size, depending on the member size, whatever material it is, maybe you can have a steel, something steel beam like that. You have a capacity of the section, that is your shear capacity. Maximum it can have. So equilibrium persists until the failure takes place. Nothing happens. Okay? When it exceeds the external force cause, that is shear force or moment, exceeds the individual capacity, then the structure will fail. And this moment capacity, shear capacity, torsional capacity, all you can calculate. Then your axial load capacity, axial load, there are two kinds. Okay? Axial load capacity. So tensile capacity, compressive capacity, they are all these capacities of the section. So in design case, if that particular section, if it cannot have the sufficient capacity to resist the force, then you increase the size. That is your design part. But at this moment, you know that as each section has its own capacity, the limit, maximum limit. Okay? So now, why I say it is both are axial, right? Both are axial force. This is tension, and this is compression. See, both are direct force. They are directly applying. The beauty of this, to find out the stress, this you just divide the force. So T divided by A will give you the stress here, or C divided by area. A is the area. A equal to area. If you divide it, it will find the stress. You will find the stress. You will find the stress. And this directly applied force, that force is directly applied, not by bending and shear. It goes along the axis. They are direct force, and these stresses are called direct stress. Direct stress means the stresses develop because of the tension or compression, axial force. But these, see, they are not equal. Concrete is weak in tension, very strong in compression. Concrete is about 10%. Concrete's tensile strength is about 10% of the compressive strength. is bad, is very poor. 10% of the compressive strength. Concrete tensile strength. Is almost 10% of compressive strength. It's very poor. Similarly, in steel is weaker in compression. Even steel is very strong, but what problem is we use some very thin members in for tension they are okay. They are very strong. So small sectional size will work. But what happens when the compression there, they try to buckle. So you cannot put a lot of stress there. Once you put the stress, it starts buckling. So it cannot take all the load. So compression wise, steel is not good. Steel is not very good. Not good in compression. Because of the size of the member. They are thin. You see, you can use angular section, steel, angular section. You can have joists like that, A section, everywhere. They are thin, they are not very fine. If you have a long strut or column, short is not a problem, but it's very long, then they will start buckling, deflecting like this. And I'll talk about that, the compressive strength. There are a lot of things you have to discuss on column. So there you will find that this steel is not good in compression. Okay? So our point is now what happens? We should have our design should be such that it should not exceed the capacity of the section. Now we have again come back to the original discussion last time. We have got the axial force Fx, we have got the rotation Mx, we have got that is the axial, that is the shear along, this is the G axis, this is the X axis, this is the Y axis, Fz, there is a rotation around or force around this one, Fx, Fy, then rotation around this, okay, rotation around that, around Y axis, and rotation around that, around G axis. So all these forces, so it is your My and Z. So all these forces, suppose you have a fix here. So for this Fx, you have got the Rfx reaction for that. So what happens if you add Fx and Rfx, both are equal and opposite, it should be 0. That means the equilibrium equation says that summation of Fx equal to 0. Similarly, if you X there is a reaction going there, opposite direction of Z, or Y also opposite direction, there will be reaction on this support, R, Fy. So this and that will neutral each other, together they are 0. force and reaction. So we have got another equation, Fy equal to 0. Similarly, in the Z direction or Z direction, we have got a force. This is Fz. If you have support there, this is the force. This is Rfz, and Rfz and Fz neutralize each other. Okay, so it is also Fz is 0. Similarly, you can write Mx same way. Mx equal to 0, My equal to 0, Mz or Mz equal to 0. So the summation total plus minus algebraic sum. So total we have got the 6 equation. This equation is called static equilibrium equation. Static equilibrium equation. But this is the case of a three-dimensional space. But for simplicity, if we take only x and y axis, just you consider only f and y axis. So f and y axis, what will remain? Your fx and fy, and try to rotate something around g and z. These are the three equations remains. If you have something there for plane frame, forget about the z. Z is not there. But thinking z is there, you cannot rotate against y, because when you rotate against y, it goes outside. But you can rotate around. If you cannot rotate around y, because the two-dimensional plane, but you can rotate around something around this, because it will bend like that. So that is around the, actually it is not shown, but it is z-axis or z-axis. So, and that is there is reaction there, all these, for all these, like earlier, we can write, what we can write? Fx equal to 0, summation of fx equal to 0, summation of fy equal to 0, and summation of moment about g-axis equal to 0. So we have three equations. So for plane frame like this, only we can have, what is plane frame actually? It is just like a board. It has not a third dimension. You see, this board doesn't have the third dimension. It's flat. So the three equations that is applicable to a plane structure, plane frame like that, or plane truss like that. These are called plane because they do not have a third dimension. They have only, they confined to the x and y plane. This is truss. So they have where these three equation of equilibrium, static equilibrium. Is applied for this type of plane frame. Okay? So 6 for the space and 3 for the plane frame. And this will be very much useful for or for finding the reactions on the beam. Reactions in a truss also. Because, you see, look here. This is a truss which has got a vertical equation. This is vertical reaction. This is vertical and horizontal. You have got three equations you can apply. See, interesting. You have got 4x plus 2y equal to 8 and 6x plus 9y equal to say 27. Take it that way. So, why you can solve x and y, right? Correct? Because you have got two equations and two unknowns. It's mathematics. Now we have got the three unknowns. These reactions we do not know. We know the force. Say it is say 8, this is 7, like that. Whatever it is. You can say it is you can say it is mega Newton, or you can say it is kip. In United States they call kip. Whatever it is, whatever forces, it doesn't matter. You can find out this reaction. This is vertical R1 V and R1H and R2. These three equations you can calculate because you have got a three equations. These three unknowns you can calculate with the three equations. Summation vertical force equal to summation of horizontal force is 0. X is in a horizontal. Summation of vertical force equal to 0. Y is vertical, and moment at any point, bending moment, which is actually the z direction or z direction, that is 0. These three equations and three unknowns, this can be easily found out. This can be easily found out. So this is the beauty of these equations. But if it is someone more, if you have something like this, it is also pin jointed, then you have got the whole unknown, 1, 2, so there is a V part also, R to V, R to H. So you cannot find out the fourth reaction you cannot find. So you cannot solve it directly, but there is a way to find it out. This is not the end of the world, okay? So we can do something later, I will tell you. Anyway, so this is all about the use of these equations. Static equilibrium equations. 3 for plane frame and 6 for space frame or space structure. Okay? So again, it is not needed right now. You see, you have got 6 forces, right? Something like that. One is this one about y-axis, x-axis, and z-axis. So we have got force going like this at this point. Okay, we have got rotation like that. We have force like this, rotation around like that. So that means we have 6 forces and 6 deformation or movement. So these are called degree of freedom. So in a space frame, every node, you see, remember that node I told you, if you have element there, this is a node, this is a node. Every node has 6, they call degree of freedom, 6 degrees of freedom. This will be not needed now, but when the rotation is there, you need to find out the stiffness there, the 6 stiffness there. Similarly, every node has got the 6 degrees of freedom if it is 3-dimensional structure. If it is a plane frame like this, you do not have 6, you only have, how many you have? You've got 2 degrees of freedom, right? Probably, yes. So, total, say here, here, you cannot have this one, your rotation is there, 3 degrees of freedom. So, plane frame, it is 3 degrees of freedom, and space, it is 6 degrees of freedom. That you should remember. Okay? So, this is all for today. We will discuss the rest of the things in the next class. And I hope you understand something in structural engineering. Things are becoming more interesting, probably. I understand. And if you have any problem, just let me know. I'll be happy to answer those. And so far so good. So see you next time. Thank you very much.